The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Let's go to the fourth presentation, and I would like to welcome Vic Perry back to the podium.
Thank you. I'd like to now talk to you about another project, the use of UHPC for troughs in a wastewater treatment plant in Edmonton, Alberta. And first I'd like to recognize the co-contributor for this paper, Don Zachariasen, whose name is in the program. Don's the Marketing Director and Product Development Manager for Lafarge Precast, based in Calgary, Alberta. Edmonton, Alberta, for those of you who are not aware of the location, is nestled fairly close up to the Rocky Mountains, on the east side of the Rocky Mountains in the northern part of Alberta. And my previous presentation, I talked about a warm weather hurricane environment which demonstrated resiliency of UHPC. In this particular project, I want to talk more about the durability aspect of the material because this particular project is in a climate where in wintertime the temperatures can hit minus 40 degrees Celsius, which is what, like minus 20 Fahrenheit, more or less. It's extremely cold, and the troughs are in a wastewater treatment plant that's unheated. That means that it gets subjected to a fairly corrosive environment in a fairly cold weather environment and subject to some freezing and thawing inside that structure because it's unheated. The Edmonton treatment facility is an upgrade to an existing facility. It's in the river valley in a park area in the city and had restricted land. So when they upgraded the facility, a typical treatment plant would be a large round tank with a perimeter trough that would collect the water as the water comes into the treatment plant. The contaminated water, the solids settle out. The cleaner water goes into the trough and flows into the next sequence of treatment. And so in this case here, because they didn't have land, they couldn't build these large clarifier tanks, so they had to build a very dense clarifier system using troughs. And the conventional solution here is to use stainless steel for those troughs. So I want to show here the use of the UHPC in this environment, which is fairly harsh because this is in the primary treatment before any contaminants are removed from the treatment process. So the project was originally designed to be an all-steel structure with stainless steel troughs, and during the design process we worked with the consultant Stantec Engineering to redesign the project to an all-precast solution. So the entire structure became precast, and I call it again conventional precast, beams and columns, hollow core, load-bearing precast wall panels, and then internally in the treatment process switching the stainless steel to precast. One of the interesting aspects of this project is that the UHPC troughs were approximately 50% of the price of the stainless steel troughs. And it's a good example when you're comparing UHPC unit price of material to other materials. It isn't the unit price that necessarily drives it, but in the case of stainless steel costs approximately $50,000 to $60,000 per cubic yard. People don't normally look at it in cubic yard pricing. So when you hear that unit price, somebody would say, well, I can buy concrete for $200 a yard. Why would I ever spend $60,000 a cubic yard for stainless steel? And obviously there are good reasons why you do it. And so the unit price is not the driver here. It's the finished and installed price. And the UHPC in this case was approximately 50% of stainless steel. So it's a good example of how to use a material in a manner that's cost effective. This particular treatment plant receives 25 trillion gallons per year of untreated sewage from the city. It's a combined sewer, so you have storm as well as sanitary, which means that in peak rainy seasons you get a large influx or a large capacity of water flowing into the treatment plant. And you can see the size of the precast components here. There was a large number of precast elements in the structure. The overall cost of the project was $60 million, and there was 192 of these UHPC troughs on the project. The project was constructed between January 2005 and December 06, so it was put in service at the end of 06. So it's been in service now for several years, and one of the reasons that they use the UHPC in the troughs as opposed to, say, conventional concrete is because these troughs have to be removed periodically for maintenance of the plates that are below these troughs. So they have to be able to lift them with the overhead crane system in the plant, so weight is an issue, as well as the durability, and also when they're handling them, they're worried about impact and abrasion and that sort of thing. So there's a lot of durability aspects as well as weight that come into play in this particular project. So here's a shot of what the troughs actually look like. They're approximately 2 feet by 2 feet and 11/16 wall thickness, fairly thin wall thickness, and approximately 15 feet in length. So what are the interesting things about this type of an application? Conventional precast tolerances, when you're manufacturing precast, you have a tolerance for this type of application of -3 millimeters or +6.5. That would be a typical precast tolerance on a precast element such as this. And you can see we have a 17 millimeter wall thickness. So if you start applying conventional precast tolerances, what you find is that you have a 15% under design on your thickness, or you could have as much as 30% more material than you originally designed or budgeted for. And that has a big impact on the design properties. If you have 15% reduction in cross-section on something this small, your stress could become critical to the point where you have failure. And similarly, 30% over design has a big impact on dead load and the actual overall cost. So it's necessary to tighten those tolerances up significantly. And on this particular one, the tolerances were more like ±1 millimeter on the production. So it means that the forming system becomes much more elaborate, and I'll look at that in a moment. Now you can see these UHPC elements are brown in color. And as you saw from Ben's slides earlier, when you subject an exposed fiber, it'll corrode on the surface and it'll stain the surface. And that stain tends to be something like the color that you see in these troughs. So we intentionally added a pigment in there because we knew that over the life of handling and moving these troughs in and out over the life of the structure, and there may be a fiber sticking out somewhere along the line, and you may get some rust staining on the surface. So we figure if you make the panels rust stain in appearance, you won't notice the rust stain. So the material that was used in the design of these troughs was a material with steel fiber. It was a steel fiber matrix, ductile BS 1000. So you can see the material identity card here. And the properties, the hardened properties of this particular UHPC were very, very similar to the properties that were presented by Ben earlier in his presentation in terms of abrasion resistance, freeze-thaw, durability, and all of those range of properties. The characteristic design value here is 23,200 in compression, 1160 psi in direct tension, and E modulus is 8 times 10 to 6 psi. So this material exhibits a strain hardening property post-cracking, and hence you can see in the direct tension at modulus of rupture and post-crack is 8 MPa or 1160 psi. So there's no reduction. You can maintain that strength post-crack, even though, in fact, the strength increases post-crack. The characteristic design value is flat in terms of the strength design. So this is a finite modeling of the actual trough, and when they actually modeled the trough, the actual stress levels in this trough are extremely low. They had to model it for hydrostatic uplift as well as live load vertically from gravity. And handling stresses as well, but the stress level is extremely low. It's about 1/10 of the characteristic design value, so there's a fairly high safety factor on the stresses in service. The biggest issue here, the biggest concern was more about the handling and impact, lifting and taking out and putting back over a long period of time to ensure that these troughs would stay without cracks in them over a long period of time. So the stress analysis was very, very low and didn't really reveal. It probably could have gone thinner, but when you get down to any thinner, people start to get scared, and then your tolerances become more important. In actual fact, the dead load of these troughs was exactly the same as the stainless steel. It was around 850 pounds per piece, and the stainless steel ones were exactly the same. So that was one of the criteria in terms of the design, is maintaining the same dead load on the structure. So the manufacturing on these, because of the tight tolerances, required a very specific steel mold, stiffened and with lots of control mechanisms to ensure that we maintain that plus or minus 1 millimeter on the thickness. But in addition to that, when you cast UHPC, it's necessary to remove any restraint during the initial hydration, because even though the shrinkage is extremely low, there is still some shrinkage during the early stage when you transition from plastic to hardened property, and that's when the material is still gaining strength. So in order to ensure that you don't induce shrinkage cracking during the casting, we like to release any restraint early on in the system. So these particular troughs were cast upside down in a upside down U-shaped form, and then the top lid was closed. There was a couple of windows to top up, and then they closed the windows. And then they had some eccentric cams on either end of the form, and they just had a strap that came down over those cams from a lifting beam above. And once they filled the form, they just picked up the form, it self-rotated, and then once it got to about 5,000 psi in strength, they released the internal form, and then they wrapped it in plastic to prevent dehydration and allowed it to cure, supported with the outside form. And that allowed for the shrinkage to occur, any shrinkage to occur without inducing cracking. It kept the moisture in for hydration and supported the material until it had sufficient strength to lift it out. And then there's 4 lifting holes, 2 in each end. They just hooked onto those, lift the piece out of the mold, and stored it. So this really just shows an overall shot of the project with the troughs installed. The plant went into service in 2006, and so far it's not that old relative to the overall life expectancy of the project, but everything is performing well, and everybody seems to be very happy with the performance of the overall project. That's the end.
Sharing another example of applying factor to our daily use, or here, I mean, not in everywhere use, is in very extreme conditions, and I'm curious, how does it look like in 20, 50, 100 years? I hope it will not change.
Look like rusty steel.
With the color pigments, this was kind of smart. Yes.
Very interesting presentation. I have a question about the design load that you're using, the design stress, 10 megapascal. Do you have any tensile fatigue information as far as how many cycles would be like under those workings? Because you will definitely have microcracks in the system at those stress levels.
Yeah, the actual design showed a service stress of about 1.25 MPa, I think, in tension. And we have a first crack at characteristic value at 5 MPa, so there's a safety factor of 4 on the first crack in service. So it's a very low stress level, and we don't expect to see tensile cracking under service load. There has been tensile fatigue testing done. A number of organizations have run some. Georgia Tech, for example, ran some extensive tensile fatigue testing. There's been a lot of fatigue testing done in general on UHPC. I know Ben Grable of Federal Highway's done a lot of fatigue testing. There's been a lot done in France as well in a number of applications. So And some of the state DOTs have done some as well. So there is a fair bit of information available on that.
Are they published?
Yes, most of it is. Now, some of the academic stuff at the university would be, you know, PhD theses or something, which, and a lot of them have put into papers in different conferences, so most of it should be published.
As far as, this is also for, with the steel fibers and its staining on the concrete surface, has it ever been discussed to use a sealer to help prevent the steel fibers staining the surface?
Yeah, we do use sealers from time to time on projects for a whole series of regions, and that is one. If you have an architectural application and you need the extra high tensile capacity for the design to give the slender look, you can seal it. Now, the other option you have is going to stainless steel fibers as well, and it's been used on a few projects where we use stainless steel, but the stainless steel fibers are a little bit more expensive, so it drives up the unit price some more. But in that case, you don't have to worry about staining if it's an architectural piece. There's a bridge done in France that has white UHPC with stainless steel fibers, and the reason is that they want it white, and they didn't want staining on white. Architects don't like stains on their panels. So, yeah, and sealers do work. No question, we have used them before.
The stresses here were quite a bit lower than what you were expecting or what you were capable of. Why didn't you use an organic fiber? Your other ductile version.
It's a little bit of a commercial decision because when the project went to tender, it was tender with two options, stainless steel and UHPC. And once the contract was awarded, the contractor came back with a value alternative of a GFRC. And he was offering them a saving. And so then the durability debate came into play. And so we didn't want to enter into that durability debate on PVA versus glass fiber. And we felt much more comfortable with the steel fiber versus glass fiber. And so for a commercial reason, and to keep it simple for the consultant as well, because they didn't want to go into that argument either with the owner. And that was the prime reason. Now, in this type of environment, long term, we haven't modeled the PVA fiber in this type of a corrosive environment. If you were to crack it, you know, long term, 100 years from now, we don't have probably the same level of confidence on the durability as we would in that particular environment as we would with the steel fiber.
I have another question. So I saw these forms that are very thin and the troughs are very thin wall thickness. So also the material is very flowable, probably flowed in. I like it because cast upside down. What did you observe about fiber orientation? Obviously they might be oriented in this wall, and then especially in the corner here, was this a weak link that the fiber needs somehow to bridge through this corner, or is there something where they are oriented and then you don't have fibers lining certain material and then it cracks easily there?
Well, we didn't have any problems with cracking on those corners, again, because the stress levels were so low. There's no question that it's going to disrupt the fiber orientation as it runs over, but the placing technique that was used was starting at one end and allowing the material to flow as uniformly as possible down over the sides so that you would have a little bit of a preferential orientation that went in the direction perpendicular to the length of the trough, which means it would have the fibers preferentially oriented in the direction to give it the maximum strength at that 90-degree angle.